So in this chapter, we're going to be looking at chi-square testing. Those of you that have taken AP Biology, you are a little bit familiar with this. So why we're going to use chi-square testing is if we have categorical variables. Like this example here is for M&Ms. And so these are my various colors of M&Ms. And these are how many in my sample I found of each color. And so this is our one-way table. It's if you guys think back to the beginning, we talked about one-way tables and two-way tables and things like that. This is our one-way table displaying, and it gives our distribution of our single categorical variable, which is color. Okay? And then it gives all of our information about the individuals in that particular sample. And we're going to use the chi-square test, which is represented by, so this is a chi-square test, which is represented by like a fancy X squared. So we're going to do a chi-square test instead of a significance test, because if we were going to do a significance test, we would have to do one for every single color. So in this instance, we would have to do 1, 2, 3, 4, 5, 6 different significance tests, and that's very inefficient when we can just do one test that would cover them all. And the significance test wouldn't give us the likelihood of getting the distribution of all of the colors. We would be looking at just one color at a time. So when we're doing our chi-square testing, what we're doing with this is we are comparing basically our observed, so what we actually saw in our sample, we're comparing to what we expected to see in our sample. This is a kind of significance test, so I'm still going to need to do a null hypothesis and an alternative hypothesis. Okay, and these do not necessarily have to be numerical, where before we would have, our null hypothesis is p equals 0.5 or whatever. Okay? When we are doing our null hypothesis, alternative hypothesis for this, it has to be in context, but it can be basically in words, and you'll see what we mean as we get to some more examples with this. But when you're doing your alternative hypothesis, it will always be that the null is not correct. You won't have any of that, that it's greater than or less than. Okay? It will be that the null is not correct. And of course, it will be in context. So if we're going to be comparing our observed to our expected, then we need to know how we're going to be counting our expected. So if you look at your chi-square statistic, this is how we get it. Okay, so this is our formula for it up here. So chi-squared equals the sum of the observed minus the expected squared over the expected. So basically you have to do this for every single one. So for each of the M&M examples, we would need to do for blue, observed minus expected squared divided by expected for blue. Observed green ones minus expected green ones squared divided by expected green ones. And we would do that for brown, red, orange, yellow. We would need to do that for every single color that we had. So when we are calculating our expected, the expected always come from the null hypothesis. Because remember, when we do a significance test, we're assuming that that null hypothesis is true. So our expected are going to come from our null hypothesis. Okay? And the more our observed differ from the expected, the more support we have to reject this null hypothesis. So like let's say I expected to see 5 green M&Ms and I see 35 out of a sample of 60, I am getting a lot more support for rejecting that null hypothesis. Okay, so as a basic rule, we're going to find our expected by multiplying our sample size by the proportions that were in the null hypothesis. So, for example, here with the M&Ms, it says that Jerome's class collected data from a random sample of 60 M&Ms, milk chocolate candies, calculate the expected counts for each color, and to go ahead and show our work. So based on the information that you can find on the M&M's website, the expected percentage of blue M&Ms is 24%. So we would take for blue, Okay, so we're doing blue would be equal to 0.24 times 60. Remember, we had a sample size of 60 in the previous in that previous one-way table there. So that's how we'd find our expected for blue. And we'd apply all of the proportions that you can find on the site there. So orange says that it is 20%. So that would be 0.2 times 60, which would be 12. Green tells you it is 16%, so 0.16 times 60. That just became a big mess. So 0.16 times 60, which gives me 9.6. And then yellow is 14%. 0.14 times 60, which gives me 8.40. And then we're going to come up here on the side. Red is 15%, so 0.15 times 60. I'm sorry, it's 13%, which gives me 7.80. And then brown is also 13%. So this is how I would find my expected values here, is I'm applying my values that M&M's claims it to be from the Mars website, and I'm applying those to my sample size that I got. And so I would use these to compare. I would compare these numbers to my observed. So now I can use these expecteds to actually calculate my chi-square data, or my chi-square statistic. So we would have our chi-square is equal to our observe minus expected squared divided by expected plus, and then we do it for every single one. Remember, when you're kind of in a rush on your test, I could ... that and type all that in my calculator so that it will spit out. But I don't have to write every single one of those categories. I can start and I can go ahead and finish. And so my chi-square value is going to be the sum of all of those, which when I do all my subtraction and squaring and dividing, I end up with a sum of 10.18. And this is my chi-square statistic. And so when I have a large chi-square statistic, I basically have two choices. That the claimed distribution, so for instance the claimed distribution by M&M Mars is correct, and these differences are just due to sampling variability. You know, I just by chance happened to grab a sample that had a lot of green ones or a lot of red ones or whatever it is that's way off. Or my other option is that the claimed distribution is incorrect, and that as you know, Mars fills their bags of M&M candies, they're not putting 13% red ones in there or anywhere close to that. So with that large chi-square value, those are kind of our choices that we have, that were due to sampling variability, or that the distribution is incorrect. So our chi-square distribution is different. It's not a normal distribution. Okay, so chi-square distributions have no negative values. So they only take on non-negative values, which makes sense if I've gone through and I've squared everything and then added it up. And it's skewed to the right. Okay, so our chi-square distributions are skewed to the right with only non-negative values. And your chi-square distribution, like a t-distribution, is specified by your degrees of freedom. And so your chi-square distribution is based on, your degrees of freedom are based on the number of categories minus 1. So for our example with the M&Ms, it would be how many different colors of M&Ms were there, how many different categories, minus 1. And so our degrees of freedom, as those degrees of freedom go up, which you can see on here as we get up to the degrees of freedom of 8, the skew becomes less, and my larger values become more probable. Right? I have in my larger values here, I have more area under the curve, than I do in my smaller degrees of freedom. So the skew moves less to the right, they become less skewed, and their large values become a little bit more probable. The mean of a chi-squared distribution is equal to the degrees of freedom. Okay, so the mean of a chi-square distribution is equal to the degrees of freedom. So in this example here that I have with the three curves, over here the mean of the turquoise curve here, it would be 8 because my degrees of freedom here is 8. The means of the one with S is number 4 here, okay, degrees of freedom 4, that would be my mean there at 4. Remember, when I have this skew, the mean is not always at the peak, right? In the 8, the mean is coming closer to the peak because the skew is becoming less. So the mean of the chi-squared distribution is equal to the degrees of freedom. The mode, okay, the mode is for the, as long as the degrees of freedom are greater than 2. So the mode of a chi-squared distribution, again, when the degrees of freedom are greater than 2. So this would not apply to that very first curve right there where it says degrees of freedom equals 1. So if the degrees of freedom are greater than 2, then the mode is the degrees of freedom minus 2. Okay, so for example, the mode for this one here would be 8 minus 2, so the mode would be 6. The mode here would be 2. 4 minus 2. I can't do the mode and the degrees of freedom equals 1 because I need to have at least 2. So when we're getting p-values from this, because we need our p-value, right, to determine whether we accept or whether we fail to reject or we reject. So we get our p-values. Again, p-values are the same as they were before. They're a probability, right? Looking at our curve, and so they're a probability that something will occur or something more extreme will occur. You can get that from technology, or we can get that from table C, which is on your formula chart. And so our chi-square density curve is a pretty good model for the sampling distribution of the chi-square statistic. So you can see that in this picture over here. So it's a Fathom dot plot simulation, 500 simulated samples of size 60 candies. Okay, and we calculated the chi-square statistic for each one of those samples. And the density curve over here, right, our degrees of freedom curve, is going to be is going to be a good model for that chi-square sampling distribution, as long as our expected counts are at least 5. Okay, so as long as we expected to see at least 5 of every different color M&M. And so in this particular example, here's our value right there. So that's our chi-square value. And so we could be looking at the probability over here, which looks like we'll get kind of a decent size p-value off to the side there. So speaking of that p-value, here's our official example for it. So you computed the chi-square statistic in the random sample at 10.18, and now we're going to find the p-value. All of our expected counts were at least 5, so my chi-square statistic will be modeled by the chi-square distribution, where the null hypothesis is true. Our degrees of freedom here are 6 minus 1, because there were 6 color categories. So 6 minus 1 equals 5. And the p-value is the probability. So again, when we're interpreting p-value, it is a probability, same as it was before. A probability of getting this particular chi-square value as large or larger than 10.18, because that was our chi-square value, if the null hypothesis is true. So given that the null hypothesis is true, so the distribution that Mars and company says, okay, I'm looking for the probability of getting a value of 10.18 or larger, okay, when I run my chi-square test. So this is, I'd be looking for the probability here under this chi-square curve. And so I can do that either using table C or using technology. I will show you table C, although I have a feeling you'll use and we'll show you technology, and I have a feeling you use technology more often because it's just a little bit more precise. So we would, if we're using table C, we would head for the degrees of freedom row of 5, and our chi-square statistic is 10.18. So 10.18 falls between these two. So I have a p-value between 0.10 and 0.05. So it's between there. I can't narrow it down much more than that. So if I'm doing it on my calculator, then I can second vars distribution, okay, and then I choose this chi-square CDF. Okay, so chi-square CDF. My lower value is my chi-square statistic, and upper value is a big giant number. They chose 10,000. My degrees of freedom were 5. And so that gives me a much more precise p-value there of 0.07 instead of saying it's between 0.1 and 0.05. So when I'm ready to truly run my chi-square test for the goodness of fit, I'm going to need to make sure my conditions are met just like I had to before. This is an inference problem, so it is going to do that 4-step method. You're going to state things. You're going to state your hypothesis. You're going to define any parameters you need to define. You're going to give your plan. Okay, I'm going to use the chi-square test for goodness of fit, and I'm going to check these conditions. And then I'm going to do my calculations, and then I'm going to come to a conclusion. So the conditions are the same in the randomization, the same that if I'm sampling without replacement, my sample size needs to be less than 10% of the whole. My large counts is a little different here. Okay, I have large counts, just like I did for proportion, because I'm working with proportions here, right? I have large counts just like I did from proportion, but I'm not looking at, before I had NP, right, and N times 1 minus P. I'm not looking for those. I'm just looking that all my expecteds are at least 5. So every single category has an expected of at least 5. And if that is true, then I'm all set and I meet my conditions there. Okay, so we're going to do one big chi-square example all the way through. So go ahead and pause for a second and read the problem so that you know the context and you know what's going on, and you can try to solve the problem as we go through. So I have categorical data here in my one-way table. I've got these birthday months here, these quarters of the year that they have, and they have gone through then, and they have counted how many players have birthdays in each of those particular groupings of months. Okay, because these problems are long and I was trying to make it not get so messy, you may want to stop periodically so you can, get everything down as you solve it. But we're just going to kind of go through this solution that's typed, and so it'll be hopefully a little bit easier for y'all to see. So again, this is an inference problem. So I need to start with my statement, and it is a test. I'm doing a significance test. So I need a null hypothesis and I need an alternative hypothesis. So there's a couple of ways that I can word that null hypothesis. I can just say that they are evenly distributed. This goes right along with it has no effect, right? Well, if you've been in AP biology, right? These are evenly distributed. It doesn't matter what month they're born in, okay? Or if I wanted to make those, if I wanted to make it a little bit more numerical, right? There I have quarters here, right? So the birthdays in January through March, the proportion of birthdays between January and March, between April and June, is equal to the one in April and June, which is equal to the proportion of birthdays that happen July through September, which is equal to the proportion of birthdays that happen October to December, which is all equal to 1/4. And if I wrote that like that, then my alternative hypothesis would just be that at least 2 of the proportions are not 1/4. You would never say that they are all wrong. You would just say that at least 2 of them, because if one is wrong, that throws off another one, right? So you just stick with the 2. At least 2 of the proportions are not 1/4. If you did it in more word format, like it is up here, then you would just say for your alternative, they're not evenly distributed. Okay, it's not the null hypothesis. Okay, but again, make sure you're using your context like always. And because this is a significance test, I need to specify my alpha. And my alpha in this case would be 0.05 because they didn't give me an alpha. So I'm done with my state part. I've done my hypotheses. I've put in my alpha. So now I would move on to the plan. So the plan, oh, why are these hooked together? Okay. So the plan would be to perform a chi-square goodness of fit. So I have to make sure I'm going to say what method of inference I'm going to use, right? I'm using a 2-sample z-test, so I'm using a chi-square goodness of fit if my conditions are met. So remember, my conditions are that it had to be random. And if you go back to the problem, it told you it was a random sample of NHL players. You had to make sure your 10% conditions were met. So I'm sampling without replacement. So that means I had to have at least 800 NHL players because my sample size was 80 players. So my population had to be at least 800 NHL players. Okay? And it says when the data was collected, there was 879. And then we need our large counts. Remember, our large counts for a chi-square test is that every expected would be at least 5. So if I took a sample of 80 NHL players, and I'm distributing their birthdays evenly across the 4 quarters of the year, then 80 divided by 4 would be 20. So all of my expected counts are at least 5. So my expected here are 20. So then I'm going to move on to the do. So for the do, I need to calculate my test statistic. I need to use this chi-square formula here of observed minus expected squared over expected, and then I'm going to sum all those up. I'll show you in a minute how to do this on the calculator. Okay, but again, if you're doing it by hand, okay, this one doesn't have as many because it's only 4, but remember you could kind of ... that to finish that up so you don't have to write every single one of those. Okay, but as I go through and I take from my one-way table that I had before, I take my observed minus my expected, I square it, and then I divide by the expected. My O minus my E. For every single quarter, I calculate this and I add it up to get my actual chi-square statistic, which is 11.2. From there, I need to find my p-value, right? So like any other significance test, I need to, when I'm showing my work, right, I need to show my statistic and I need to show my p-value. So I can use, so if I looked at my distribution here, if I looked at my picture, right, this is my chi-square distribution. It's got a pretty strong right skew because it has a low degrees of freedom. My degrees of freedom are 3 because I had 4 quarters of the year, right? So 4 minus 1 gives me 3 for my degrees of freedom, right? Which means my mean for this would be 3. Okay, and I could calculate my mode for this as well because my degrees of freedom are greater than 2. So my mode for this one would be 1, right? 3, my degrees of freedom minus 2. So I'm looking for a probability that I got a chi-square statistic of 11.2 or greater because I can use the chi-square distribution for this just like I can use a normal distribution because my conditions were met. So I want to know the probability that I get a chi-square, because it's what my p-value tells me, right? The probability that I get a chi-square value of 11.2 or higher to the bigger extreme. Okay, and so I can use table C to find that, or I could go ahead and use my technology. If I'm using table C, I am at, see if I can pull this whole thing up. There we go. So if I am using table C, I'm in my degrees of freedom is 3 row, and I find my chi-square value falls in between here. So my my p-value is between 0.02 and 0.01. So I'm writing those 3 things down. If I've used my calculator, which again we'll show you how to do it, I've made sure I've written those down. My degrees of freedom, my p-value, and my chi-square value. My conclusion will need to be in context, like always. So, and I'm going to interpret the significance test like I always did. Because the p-value, which was 0.011 when I find it via technology, because the p-value is 0.011, is less than the alpha of 0.05, we reject the null hypothesis. If it was greater than 0.05, then I would go ahead and I would fail to reject it. But I have a very low p-value here, so a very small probability that this would be due to chance, that I would get these particular distribution. So we have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. Now, you did not narrow that down to say that there are more of them in that January to March. You're just saying that they are not evenly distributed because that's what your alternative hypothesis was. It's just that they are not evenly distributed. So the last thing we want to look at here is if you chose to do this on the calculator, what would that look like? So if you choose to do it on the calculator, then you're going to go to Stats and you're going to go to Test. And it's the Chi-Squared GOF test, Goodness of Fit test. You enter the counts, list the observed counts on list 1, the expected counts on list 2. So basically, this is list 1, this is list 2. So I get the observed in list 1, the observed in list 2. So when I go to the goodness of fit test, I can tell it that my observed are sitting right there in L1 and my expected are sitting there in L2. I need to know how to calculate the degrees of freedom. 2 minus 1, 18 minus 1, 4 minus 1, whatever it is. So I need to calculate the degrees of freedom, and then I need to go ahead and have it drawn. So it'll give me my goodness of fit test. It'll give me the p-value. It'll give me the test statistic, the chi-square statistic, and it will remind me again of my degrees of freedom. And if I wanted to draw it, it would show me that all those non-negative numbers, that right skew. Again, like always, you run a risk when you only use your calculator on the AP exam. You need to make sure that you're showing all those, you're giving all those values there. And you're going to want to name the procedure on your calculator. You're going to, again, need to make sure you name the degrees of freedom, the p-value, and the statistic. And that's it for section 1 of chapter 11, our next to last chapter.